start from the session, if you agree. Even because Javier is with the long trousers and not so good. We don't have we need to suffer too much for the time. So now let's go on with the second talk of today. That is a smart computing continuum or smart environment to Javier. Thanks for coming.
Thank you very much for the presentation. Good afternoon, everyone. I'm going to start the talk. As Massimo said, my name is Javier Berrocal. I'm from the University of Extremadura, and as you may know, Extremadura is a region in Spain. Lupe presented before Berrocal disease. Probably, if you don't know Berrocal disease, probably you don't know where Cáceres is and where Extremadura is. So I will start presenting where Extremadura and Cáceres, my city, is. Extremadura is a region located in Spain. It's close to Portugal and just in the middle between Lisbon, Madrid, and Seville. And it's a very big region, and it is just in the middle of these three big cities. Many of you probably don't know where Extremadura is, but now you might locate it in the map. I'm living in Cáceres, which is the city that is more or less just in the middle of Extremadura. Extremadura is well known for the cultural heritage because it has three different cities that have been named for the cultural heritage. It is Cáceres, Mérida, and Guadalupe. This is Guadalupe, which is the village where I was born. That is Cáceres, where I'm living right now, and that is Mérida. So if you don't know Extremadura, I invite you just to come to Extremadura and maybe just to visit us, to visit the University of Extremadura and our research group. Or if you want, we can also organize a conference there, and then it will be easier for everyone just to go there to Extremadura. I belong to the campus software engineering group, which is a very big group. Currently we are more or less around 30 PhD, and we have a lot of PhD students. The campus software engineering group has a lot of research line, focus on big data, open data, Internet of Things, social and pervasive computing, and most of these research lines are developed with the focus of software engineering. As we are a very big research group, we mainly focus on, as we are a very big research group, we have different labs, and these different labs focus on different research lines. I belong to the Social and Pervasive Innovation Lab, which focuses mainly on Internet of Things and social and pervasive computing. And this is the lab, the SPI lab, the Social Pervasive Innovation Lab. Currently we are around 17 researchers, 10 PhD, 7 PhD students, another 7 students more or less that are working with us. This is some old picture. Some of the faces changed because this picture has a couple of years more or less. But the good thing is that the lab is increasing and the number of people working with us, the number of PhD students increasing every year. And we focus on different research lines. We focus on mobile computing, cloud computing, and mainly on the computing continuum and the quantum computing. And we try to apply this research to different domains, which is Industry 4.0 and gerontology, which is just to improve the quality of life of other people. So once I introduce more or less my labs and my university, I'm going to start with the talk, which is a smart computing continuum for a smart environment. I added one more, which is toward a smart computing continuum for a smart environment, because I will present the different things that we are currently working on, and we are just in the path of making the computing continuum a little bit smarter. So during the last few years, we have been defined. We saw how the number of IoT devices that are currently deployed on the environment is increasing. Every year, the number of IoT devices devices is increasing and is increasing a lot. If we analyze this number, how this number is distributed in the different domains, we can identify that this deployment of IoT devices is focused mainly on different some specific domain, focus on industry with the industrial IoT, on the enterprise IoT, in the smart home, in the connected vehicle, and also in the smart home. Are some of the main domains in which these IoT devices are being deployed. Usually, these IoT devices has a similar pattern. All of them are deployed. They send different information. This information is sent to the cloud, and that information is processed on the cloud. And then different actions are sent from the cloud to the IoT devices that should to change the environment and the situation, the behavior of these IoT devices. But if we analyze some of the requirements of the domain in which these IoT devices are being deployed currently, we can identify that they have some important requirements focused on the real-time capability of this environment, or the low latency, or the privacy and security of the information that is sent and processed. So these are very, very important requirements that sometimes they are very, very difficult to achieve with this pattern, this behavior in which all the information is sent to the cloud and processed on the cloud. So during the last few years, we have been working on different paradigms, focusing on the fog computing, in which we are able just to deploy servers closer to the end user, and this server can compute some of the information. That information doesn't have to be sent to the cloud. Or we have been working on the X paradigm, in which we have different devices at the edge of the network that are also able just to process different information. In the end here, we have different layers that each layer is closer to the end devices. So we are able to process that information in a layer that is closer to the end device, so we improve the privacy, we improve the latency, and the responsiveness of the IoT application. So in the end, what we have is all these layers connected, so the IoT devices can send information to the edge, to the fog, to the cloud, and that information is processed as soon as possible. But one important problem of this complex infrastructure is we have this infrastructure, but now we have to develop applications for this infrastructure. We have to develop applications that will be able to use this infrastructure, and should be highly distributed applications. So we need to solve some problems, some issues related with that. So we need to solve how these applications are developed, how these applications are deployed, how the different resources of the different computing nodes are managed, because we have a lot of computing nodes that we have to control and we have to manage. What happens if the quality of the service changes? Because probably it will change along the time. So something we will have to do. If we analyze the cloud computing infrastructure and how it has evolved in the last few years, we can identify that companies are using every year for this infrastructure. We are using this infrastructure for almost every application, but they have one important problem, which is optimize the use of this infrastructure. Optimize the use of the cloud computing infrastructure. And if this is the goal with the cloud computing infrastructure, once we have all this complex environment with the computing continuum or the cloud continuum with the cloud, fog, and edge computing node, it will be even more important just to be able to optimize the use of this complex infrastructure. So what we identified is that we need new methodologies and we need new tools that should be able to guide developer, operator, and also the stakeholder and the user just to use this complex infrastructure. And trying to analyze these methodologies and this tool, we identify that currently people that are developing IoT application and distributed application follow this methodology, the DevOps methodology. Almost most of them are using this methodology currently. So what we did is to modify a little bit. We are working on right now define a little bit this methodology to include different activities and different practices just to improve how the developer and the operator and the user are able just to interact with this competing continuum infrastructure. The DevOps methodology has a lot of phases. We have to plan, code, build, test, release, deploy, operate, and monitor our application. It has a lot of phases. Some of them have to be changed and have to be evolved to be able to control the computing continuum and the application that are deployed in this computing continuum. Here I have highlighted some of them, which is some of the phases in which we have been working on during the last few years. We have been working on also in other activities, but those are the ones that I want to highlight for this presentation. We have been working on the planning phase, in which we have been working on how to create a deployment plan, or in the testing phase, trying to create an application a framework to emulate the real computing continuum environment, or on the operate phase to create elastic data or on the continuous or on the monitoring phase just to create a continuous adaptation practice. So focusing on this methodology, the first thing that we have to do when we want to develop a highly distributed application is to plan the application. We have to plan how to create this application, how to modularize this application, and then we will be able to start building the application. So if we analyze this first phase for the computing continuum, we can identify that there are a lot of dimensions that we have to consider in order to plan to design an application that has to be deployed in this computing continuum. One of these dimensions is the application. We have to be able to analyze the application, the different services that compose this application, the connection between those services, different modules that we need to create these applications, such as aggregator, orchestrator, service discovery, roles. And that is one of the dimensions that we have to analyze to be able to deploy the application. But also there are other dimensions that we have to take into account. The other dimension is the computation, or the infrastructure dimension. We don't have only the cloud environment that's to deploy the application. We have other computing nodes that we have to take into account. We have the fog nodes, we have the edge node, and we have the different IoT and thin devices. And we need to know the different capabilities of this node just to be able to identify where the different services, where the different modes can be deployed. But also we have other dimensions that we have to consider, which is the networking dimension. All of these computing nodes have to interact, have to share information. So the way in which they share information is through the network. So we have to consider the networking dimension just to be able to identify the different links between the different computing nodes, but also because now we can use this networking dimension just to deploy also different services. When we have a discovery model, maybe we can deploy this service discovery model in some of the components of the network. For example, we can deploy it in the controller. So in order to be able to achieve some specific quality of service, we need to consider different dimensions. It's not enough to just consider one dimension, but we have to consider all of them. So in this sense, during the last few years, we have been working on a service placement framework. So once we are designing the application, maybe we can just take the information of the different dimensions and evaluate the information on the characteristics of the different dimensions in order to identify where the different services should be placed in this complex infrastructure, taking into account the different services, the application, the infrastructure, and also the network. In order to do that, what we did is to define some specific characteristics that we need to evaluate the quality of the service of the application and to evaluate the different dimensions, the application, the computing, and the networking dimension. And we asked the developer just to identify that information, such as the requirement of the different services, of the different microservices, the RAM, the computing needs of the different services, but also the same for the different computing nodes. So we can just ask the developer to fill this information, and we with that information, we are able just to identify and process that information and create a deployment plan, which is where the different services should be deployed. This deployment plan also can consider different quality of service attributes. In this case, currently we focus on two specific quality of service attributes, which are the response time and the cost, which are some of the most important quality attributes for some companies. Like we have to assure that the application is responsive to the different activities and to different information sources, but also we have to take into account the cost, how much it will cost. We evaluated this framework in different environments and different configuration. We identified that we are able just to trade off the different characteristics, the response time and the cost. But one important thing is that we also evaluated the framework with a real test bed, and we were able to identify that the quality of the service that the framework defined that we will obtain with that specific deployment was really obtained. So we were able to test that the output of the framework was correct. In order to create this framework, we have been working on different mathematical models, and we use this linear programming just to be able to define different properties and to process the different properties and to obtain the optimal placement of the different services. This is good because in the end we have the optimal placement of the different services, but it has some important problems, especially one important problem. And it is that it requires a lot of time, and it is not possible to use this solution just for every environment. For very big environment, in this case for environment with more than 300, 400 computing nodes, it's really costly in time just to use this solution. So currently we work on different techniques just to evolve this service deployment framework just to be able to cover also very big environment, so more or less big environment. And in that sense, currently we are working on different heuristic and artificial intelligence technique just to be able to get this service placement framework. So coming back to this methodology that will make my presentation, once we plan the application, we have the deployment plan, we code the application, we build the application. And one important practice of the DevOps methodology is to test the application that we have developed and then release and deploy the application. Of course, we have to test that everything worked as it was defined, and that we obtain the quality of the service that, for instance, the service placement framework said that we will obtain. And this is really difficult for highly distributed applications that make use of the computing continuum. Mainly because we don't have a lot of tools. Currently, we have a lot of tools to test different applications, to test mobile applications, to test services, but to test a highly distributed application that will be deployed on the computing continuum is very difficult because we don't have a more or less infrastructure close to the real computing continuum. So how we can test this distributed application in the computing continuum? In order to solve this problem, what we did is to create a framework that is able to create a virtual environment in which this application can be tested. In this case, we follow the continuous deployment practice, and for a continuous deployment practice, usually what it does is once the code is more or less stable, once we commit some changes to the master or the main branch, then the application and the software is tested, and that is what this framework does. And what this framework does is to monitor the GitHub repository of different GitHub actions. We are able just to create a completely virtual environment. And this virtual environment is something like this, in which we have the different IoT nodes, which are completely virtual devices. For instance, we can have different mobile devices, and they are virtual devices in which we can test the application. We can also create different computing nodes, pop nodes, and nodes, and we also can simulate the different networks that connect the different devices. For creating the different nodes, we use Docker, and for simulating the connection, the network connection between different devices we use the framework Cathara. And this virtual environment is something that is built when a new chain is identified in the source code. When, again, following the continuous deployment practice, when a chain is identified in the source code, they have actually identified this chain, and then it built the virtual environment just for that specific application and with the characteristics defined for the native developer. Then, when we created this virtual environment, we deploy the application in this virtual environment, we test the application, something that is closer to the real computing continuum, and we obtain the quality of the service of the application. And in this case, we focus really on the response time of the application and the different services. And of course, if we obtain the required response time, then the application can be deployed in the real environment. And we evaluated this framework also in a real test bed, and we identified that the data that we obtained with this virtual emulated environment is close to the real one. But the problem is, are these simulated environments realistic? Of course, they are realistic for what the developer defined. If the developer defines some specific computing node with some specific capabilities, then it is realistic because we evaluated that and it said that it is realistic. But sometimes what the developer defined is not the real environment. It defines some general devices that are close to the real environment, but they are not the real environment. So, evaluating this step from the development methodology, we identify that, of course, right now we cover the test phase, the release, and the deployment phase. If we analyze the complete development methodology, we identify that there are some phases that we need to cover also just to create more realistic environment. And in this case, it is the monitoring phase, in which maybe this monitoring phase can be used to create more realistic environment. We can get information from the computing continuum, monitoring the computing continuum, to create more realistic simulated and emulated environment in which we can test the IoT and the highly distributed application. So currently we are working on evolving this framework to something similar to that, which will be a digital shadow. In this sense, we have something similar that we had before, but currently what we want to do is just to create some monitoring framework and agent that are able to monitor the computing continuum, get them that information to create the specification of the virtual environment that has to be created, and with that specification we will be able to create a digital shadow of the computing continuum in which we can test the application. And then it will be closer to the real environment, to the environment in which finally the developer will deploy the application. So once we test, release, and deploy the application, then we have the different IoT applications that are executed. So we have to operate the different application. And we have to control that application, maintain the quality of the service that we define. In the sense, when we deploy an application, for instance, that could be a smart city application, and when we design this application, we define that this application probably will use some IoT devices that are required for the different functionality of the application. But usually this is just a design, this is not the reality. In the end, when we deploy our application, what we identify is that it is not only our application that is deployed, what we identify is that there are other IoT applications that are also deployed in the environment. And that some of those applications are using the same IoT devices, are using the same data. So in the end, what we have is that we have different IoT applications. These IoT applications use some of the same IoT devices, and also they use the same computing resources. So we have IoT devices that generate the same data or some similar data, some applications that use and process that data to get a similar conclusion, but also this application that usually competes for data and also for computing So we need something to adapt the deployment of the application to the specific requirement and to the specific deployment of the application once different IoT IoT applications are competing for different data and resources. So in that sense, we have been working in the last few years in this elastic data analytic framework. This work that we started with SummerSOC, in which we evaluate different dimensions for the data analytic, the data quality, the resource consumption, the computational tools. And then for those data analytics, we evaluated two different dimensions, which is the accuracy and the freshness. And we identified that changing a little bit some of those dimensions, the accuracy and the freshness, we can have different data analytics that usually consume different resources, but also have different results. So in order to create this elastic data analytic, what we defined is to deploy an orchestrator that is able to evaluate the different computing continuum infrastructure and receive the different data analytics that the IoT application need to secure. These data analytics are received by this orchestrator, then the orchestrator sends this analytic to the different edge nodes or the different fog nodes. And these fog nodes are able just to aggregate different information from the IoT devices, but also they have attached the different information so that that information can be reused by other IoT applications. So depending on the different data analytics that we receive, this orchestrator will be able to distribute this analytic to different parts of the infrastructure. And also to evolve this distribution depending on the different analytics that has to be processed. Thus, these different resources are distributed depending on the different requirement of the IoT application. Using this orchestrator, we are able to get different data analytics that provide different results that could be close, but probably it will have more or less data depending on the accuracy and the freshness of the information. And this IoT application can use some of this data analytics to process and to secure the different functionality that has been defined. And this was a work that we funded 1 year ago, more or less. Currently, we are working on evolving this work to create some smart orchestration, why not, and a smart choreography, which probably we will not need an orchestrator just to define and change the configuration of the different data analytics. So one, we operate and we secure the application. We have to monitor the application to control that the application is executing and has provide the quality of the service that was defined. But if we analyze different applications and how different applications are executed and the response time of the different applications, we can identify something like the different channels we have here in this slide, in which as the number of users increase, usually the response time will also increase. And from an example, which is from the sticky note application, as the number of whiteboard in the sticky note application increase, also the performance of the application is reduced. So what this says is when we use an application and depending on the user that are consuming that application, depending on the different data that we have to process, depending on how the different functionality are consumed, probably the application will change and will not be stable in the future. The quality of service that we are able to obtain right now probably is not the quality of service that we will obtain tomorrow, or in 1 month, or in 1 year. So we have to continually check and monitor how the application and the quality of service that we obtain evolve. So following this diagram, what we suggest is to monitor the quality of the service, to monitor the quality of service of different applications, and if the quality of the service change, then instead of going to the planning phase again to start building the application, testing the application, and deploying it again, what we suggest is just to create a new practice in the development methodology is the continuous adaptation. In this practice, what we try to suggest is monitor the application, and once we identify that something was wrong, that the quality of service that we want to achieve is not achieved, then we have to adapt the deployment of the application in order to obtain another deployment and try to get the required quality of the service with this new deployment. And this continuous adaptation practice currently is focused on some of the methodology defined by Facebook. Facebook defines a methodology with this practice, with this continuous reasoning. And in this practice, what it says that we have to be continuously checking and monitoring the application in order to identify those parts that are broken or those parts that have been changed, in order to identify how those parts have to be fixed, and in order to identify how they can be fixed in a long time, in response. And in this end, we use continuous reasoning just to detect different modifications in the application. We identify broken deployments, and we identify quality of the service violations. In this sense, broken deployments are different deployments of the application in which, with which we are not able to execute the application anymore. So it's a parallel computing node that is broken, a link that is broken, some services that cannot be executed anymore. So we have the application but cannot be executed anymore. And the quality of the service violation are those deployments in which the application can be executed, but the quality of the service obtained it will not be as good as we expect. So probably the quality of the service is higher than we expect. So we try to identify with this continuous reasoning method the broken deployment and the quality of the service violation. To that end, what we do is just to evaluate the placement of the different services. We evaluate the current scenario with the different computing nodes, the different services that are deployed in those nodes, and we evaluate if everything is working as it was expected. And to do that, as I told you before, we are using continuous reasoning. So through continuous reasoning, if we identify that some computing node is broken, then we will be able to identify what part should be fixed. And we are able to define a new placement, a service placement method, deployment plan that can be executed to solve and to fix all the broken deployment and the quality of the service violation. So what we are trying to do is, if again we have some specific threshold for the quality of the service, for the response time in this case, and that threshold is surpassed, then we try to identify what the specific devices or what the specific part of the deployment are broken, and then we try to fix it as soon as possible. And if we are able to identify those broken parts, then we are able to fix it quicker than if we wait for a longer period just to fix the complete application.
Quick question, maybe I missed the point. Is continuous adaptation a sub-aspect of elasticity?
Currently it's not part of the elasticity, but it will be a part in the future. And currently what we are working on is just not only to evaluate the current scenario of the deployment of the application, but also some future scenarios that we can predict with different artificial intelligence techniques. So the idea is, before having a broken deployment or a quality of service violation, try to predict the behavior of the application, the prediction of the different computing nodes, thanks to the continuous reasoning, and then try to define a new service placement before having a broken deployment or a quality of service violation. And those are the things in which we are currently working on, mainly the computing continuum. And just as some conclusion, the computing continuous allows developers to have a better control of the quality of service, but that requires a lot of time, that requires very skilled workers that are able to control the network, to control the application, and then to control the different services. So we need new methodology, we need new tools that provides some help and some guidelines to the developer and to the operator just to know how to manage this deployment and this execution of the highly distributed IoT application. And artificial intelligence can help on reducing the required skill of some of this work. Probably it will be a complex environment. We will have to work and define different policies and different strategies. That is all from my side. Thank you very much for listening. If you have any question or any doubt.
Thank you.
Questions? We are thinking about it. Questions? Sharon? No. Yeah.
Yeah, thank you a lot for the presentation. I liked it a lot also because I think that our research is quite well aligned in terms of how we aim to have scalable computing continuum. I was asking myself because we are also facing a little bit the issue that we have the high heterogeneity in the computing continuum of devices, and how do you especially cover the quality of services of different, let's say, devices that the computing continuum is composed of? Do you have any type of abstraction mechanisms, how you compose, let's say, different sets of devices, or do you only treat quality of service on an overall system perspective, or also on a device basis?
Currently, for the quality of the services, we are evaluating the quality of the service of the application of the devices themselves. What we try to identify is the responsiveness of the different functionality of the application. We are not trying to evaluate the overload of the different computing nodes or the different devices. Of course, that is something that can be done for the different monitoring framework, but probably what we do, and mainly what we do in this framework for emulate the computing continuum, is just to evaluate the quality of the service of each functionality.
Thanks.
Other questions? I have one more curiosity, and I want to like your point of view. And this again, I make the same about open science principle. How it can be applied to your type of research? So do you believe that somehow if people start to share the results over continuum, what could mean to share data set over continuum that can help, for example, future design, future research? Have you ever thought about it?
No, I never thought about it, but in the end, if you start sharing data, that is some data that will have to be computed in the continuum, and we will have to be able to aggregate this data for different reasons. And probably as we use different elastic data analytics, maybe the results of computing those data can be obtained and can be stored in some middle layer just to be used for other people and for other purposes.
In your experience, did you have any difficulties if you have an infrastructure and you ask to share the data of the continuum? What I mean, the topology or the different device or the property of the device? What is your experience? Have you seen that your partner's company would allow you to share infrastructure data, or you found that they consider, let's say, confidential and not? Because I'm very curious about it. I think that if Amazon or the big cloud provider would start sharing, for example, sets on how they organize their infrastructure, this would help us researchers to create algorithms that are more up to the point. I know it's a bit provocative, but as you are more than me in the topic, I want to know your opinion.
Yes, that is a very good question, but It's complex because in the end we have different privacy issues, different security issues. And for instance, we have been working a lot during the last few years with different researchers on how to manage these privacy policies. And we make some surveys about if some companies and some people will be willing to share some private data. And we identified that they are willing to share some data, but depending on the context and depending on who will consume that data. And for what purposes does data will be consumed. But that is something that has to be controlled. In the end, if we want different people, different companies to share different data, we have to control who can consume those data and for what purposes that data can be consumed. And then if we have something like that, some framework that is able to cover those different characteristics, then we will be willing to share that data.
Okay.
If no question, I think that we have closed this section, and now you are the chair of the third section. Ciao.
So perfect. Then let me introduce the final session for today, which is the actual paper session or the third paper session of SummerSOC this year. And I think I've already seen the first presenter, which is Andrzej Javier. I pronounced it somehow right. Perfect, great. And yeah, he will bring us to also to an area which is let's say with the topic smart asterisk, smart something in the agenda today. And he will talk about some explorations about various privacy challenges regarding different perspectives of drivers and car manufacturers, which is, I guess, especially interesting. As you know, it's a MacBook, yeah, because the Mac adapter stuff.